So we have one more presentation before the break from Josh. So Josh holds BS and MS in electrical engineering from the University of New Mexico. Currently, he is a fifth-year PhD candidate under the guidance of Professor Rolando Burgos. His research focuses on medium voltage power electronics converter and the installation design, as well as system integration. Josh.
Thank you for the introduction. Good morning, everybody. So the previous two presentations did a good job setting the stage for me and kind of showing what our converter is and the circuits in it. So my piece here is going to be looking at, thank you. Yeah, my piece here will be looking at more on the system integration side of things. How do we take all of those circuits, put it together, and make it into something that we can actually pick up and ship to another place if we want to, or build it into the larger converter. And so a lot of y'all have already had the chance to come through and look in High Power 2 to see the converter. If you haven't come by during the dialogue session, it's actually pretty amazing. This work is going to be actually improving on that and increasing the power density of our power electronics building block. And I have, so one thing, I do have a lot of pictures here. You know, they say that a picture's worth 1,000 words. So I hope to say a lot in the same amount of time. And whether you're on the high voltage side of things or the low voltage side of the house, hopefully you can take away something from this presentation. Thank you. So we'll start off with the background, which has already been laid out pretty well. And then I'll show the areas of opportunity that we addressed here to increase the power density. Specifically, that's going to be a few of the PCB-based components, such as the DC bus and the capacitor daughter cards, and then the cooling system, which gave us a huge opportunity. Then we'll wrap up with conclusions. So really, some of the target applications for these converters are going to be places where the cost of space is large. And so we want to come up with modular converters so we can increase voltage or power levels in many ways. One example is just on board a ship where you have multiple loads. So in the traditional way, you'll have a lot of different types of converters that have different specifications going through different vendors. Using this approach, you would have a modular converter. Again, you can stack it up with various numbers in series or parallel to get your target voltage and power level. So again, here's our converter that we actually have in there. Again, come by and see it if you haven't already. This is 2 phase legs with 4 cells in the upper and 4 cells on the lower arm, giving us our 24 kV bus. Each of these PEBs is rated for 6 kV. All of the components were tested individually using high pot and partial discharge testing to make sure they're PD free. Then on the assembly level for the individual PEB, we put each component in and continued to test the PDIV just to make sure that as we assembled it, we didn't have some issues there. So we verified that this PEB was PD free up to 32 kV. And our power density of this is 12 megawatts per cubic meter. And so looking at what do we need to consider for the voltage level for our insulation, we want to consider the worst case operating state. And so if we look here, this represents one of our PEBs or one of our power cells. We have several of these in series. In this case, we're going to have 4 in series. And so the differential voltage inside of the cell is always 6 kV. It always blocks 6 kV. During the switching state, if we're looking at ICVT, during the switching state where the bottom switch is conducting and the top switch is blocking, then our 24 kV bus is now connected to the bottom rail of our capacitor bank inside of the PEB. Again, remember, it's still blocking 6 kV. So that means that the maximum voltage with respect to earth ground is actually 30 kV. So for this, we want to do all of our insulation design for 30 kV, even though we only have a 24 kV bus. To help out with the insulation challenges, our module, the heat sink, all of the components are referenced to the midpoint of the capacitors. So in this case, our local ground is going to be created. And for the top cell, that'll be up to 27 kV with respect to Earth. And now this is going to be important whenever we start to consider the architecture within the cell. A lot of these circuits you saw from Ning, kind of their operating principle. Again, remember that they're referenced to the midpoint of the capacitors. And so the voltage between the WPT and the fans as well, and earth ground is going to be up to 27 kV. Whereas we have several other components in here that are at 6 kV, just differential voltage inside of the cell. So what we do is we create really 4 different insulation zones, is the way that we considered this, where we have all of our auxiliary circuits primarily above the bus and our power stage components primarily below the bus. We have a few of the auxiliary components like our wireless power transfer converter below the capacitor bank, as well as our pre-charge circuit. But the real challenges here is going to be the spacing that we need between the heat sink and the fans in zone 1, because again, these fans are powered from external fans because of the power requirement for them. So this is our largest consideration here. So some of the areas that we're going to address, again, to try and improve the power density here is going to be looking at the medium voltage capacitor cans. This is, again, for the ARPA-E circuits project. We're going to try and leverage the PCB-based bus a little bit more. So we'll be addressing the auxiliary power bus, which previously in the circuits converter was just routing wires as we needed throughout the converter. The other place that we're going to look is going to be trying to modify the standard cooling system that we used before. And so we'll be implementing what we call a high voltage oriented cooling system. We'll be integrating the PCB, the auxiliary power bus within the PCB bus, and we'll be building custom capacitors to replace the standard capacitors. And so one more piece here to kind of take a look at where we're coming from on this, because the bus, for me, my part on this was really the centerpiece for how we were able to achieve the power density and integrate this so well. We started off with using a traditional laminated bus to where you have the layer stacked. This is using heavy copper going, you can get these made through several of the mainstream manufacturers. But whenever we got it, we tested the partial discharge inception voltage on it. And again, we're trying to operate this at 6 kV. We were only able to get up to about 5 kV, and we had pretty large PD. From working with the different vendors, and this same answer came from several of them, they all said that we would have to pretty much double the thickness of our insulation in order to get the PDIV that we were targeting. And that's not really acceptable because it was already heavy. It was about 17.5 pounds. And also that increases your loop inductance. So we started looking at how we may be able to use a PCB to take advantage of the mature technology and the really good insulation quality that you can get from them. This is a cross section, just an example cross section of a PCB at the terminal. You see here in this example that minus DC is connected to your via, where you make your connection for your elements. And then we have plus DC, minus DC with midpoint layers separating them. And we really utilize this fact that the midpoint layer is on the outside of the bus because, again, we're using this as a local ground. And so this allows us to put the components really close to the bus without having to worry about any differential voltage or high fields in between them. What we're showing here is kind of the geometric techniques that we implemented to control the peak electric field within these PCBs. So for instance, you may think that, okay, let's just pick a specific clearance requirement and set that in your program and then run with it. But what we're showing here is that by introducing some offset between your conductors, depending on the potential of those conductors, you can actually decrease the peak field intensity. So if you have no offset, you're actually going to be operating at your worst case. And just again, a 1 millimeter offset, you can reduce it by up to 13%. So this is just a quick schematic of the PCB bus that we started off with for circuits. A reminder of the way that it was configured, having our plus DC and minus DC layers sandwiched between our midpoint layers, which they're called here 0 volts, just because we're using that as a local ground. What we ended up doing is saying, hey, we have a PCB. Let's go ahead and add a 48 volt layer on there. The voltage is very low between these. So we can add a 48 volt layer into this PCB for power distribution for all of the auxiliary components. And there's a very low penalty to the thickness and even the cost of the board. By adding these two 48 volt layers, it only increased the thickness of the bus by 0.5 millimeter. So this specific bus is 16 layers. We have several layers in parallel for helping out with the higher current through the board. So we have 4 parallel layers for the plus DC and 4 parallel layers for the minus DC. We also implemented surface mount connectors on here. So once we do all of our field analysis for the converter and determine where we want all of our components to be placed, then we can just simply put surface mount terminals on the bus, and that gives us a direct connection to the 48 volt auxiliary power bus. And so it eliminates any of the high voltage wiring that we previously had running throughout the converter. And so a quick take on our test bed. All of our testing for high voltage is done inside of a shielded room. So we have an AC supply outside of the bay. We also have a plus minus 25 kV PWM source that we can use if we desire. And inside of it, we're measuring the partial discharge using an MPD 600, which allows us to capture or generate this phase resolved partial discharge plot. And this is used to plot out individual discharge events versus the phase of the excitation in which they occur. And by looking at the pattern that we have, we can start to get insight of, okay, is it happening inside of the dielectric based on it being, more near the 0 volt crossing, or is it occurring somewhere in the air, being somewhere near the peak of the excitation? We also use optical techniques to be able to capture and locate where the discharge is occurring if we can see it in air. So we have a silicon photomultiplier diode to capture the light, as well as a digital camera, so we can again locate those locations. So for the bus, we tested it on a layer-to-layer basis to check the insulation of each individual layer. And our target PDIV on this was above 3 kV per each layer, because again, remember the maximum differential voltage between any 2 layers is only 3 kV because we have that midpoint layer between them. And we're trying to target less than 10 picocoulombs apparent charge. So with this measuring between each layer, the PDIV was about 6 kV, which is more than 2 times what we're going to have on there. So with this, we were able to verify again that this PCB-based design is functional. We took the same approach to designing the medium voltage capacitor cards using heavily the E-field analysis on this. And this really gave us the opportunity to take advantage of surface mount components for balancing resistors, again, reducing the medium voltage risk of the converter, allowing us to get higher power density out of it. And we do the testing here, not only to check the PCB itself internally, but also to check the spacing between the terminals. We can see that within the board, we were able to get our target again of 6 kV, so double the voltage, and no discharge occurred up to 10 kV when measuring between the terminals. And it's only going to have 3 kV, so we're more than sufficient there. The next part that we're going to address is the cooling system. For the circuits converter, what we did After we ended up testing all of the parts in the full assembly minus the fans, we added the fans and adjusted the height so we could determine exactly what spacing we needed in there. In this case, we looked for those individual discharge events to see where we started to have the discharge. What we determined with this is that we needed to increase the spacing from what we originally thought would be 42 millimeters. We had to increase it to at least 108 millimeters just to get PD-free operation. And a large part of this is going to be, one, because of the heat sink itself, but then also because there's non-idealities in the fans that we hadn't accounted for at first, such as circuit boards, your motor casing, as well as wires. So we really wanted to look at how we can improve this. And well, if we look at just a typical heat sink, you know, it's kind of as expected. You're going to have your fill enhancements on the corners of the heat sink because of the sharp points. So what we did is took a page out of the medium voltage playbook and we implemented a corona ring. So we can see that by using a ring around this heat sink and fixing it to the same potential as the heat sink, we can shield these corners and smooth the E-field around it. And by doing this, we're able to reduce the peak field intensity by about 50%. The other thing that we looked at is the heat sink itself. You know, you may ask, well, why don't we just go ahead and round the corners? And that's exactly what we looked at. So we looked at how changing the radius on these various corners affects the field intensity. And what we found is that you can just arbitrarily pick a radius that you want to go with, and it will help most of the time. But that's not always true in all cases. And so there are cases where if you pick the wrong radius, basically you create a knife edge, if we want to imagine it as that, like what you see here. And you can actually end up worse than you were before. So we came up with a design guide pretty much with what not to set it at. And then if we round these corners, then we can again reduce the peak field intensity in that way by 50% as well. So this is showing a comparison of two heat sinks, one without the rounded corners and one with it. And just here you can see again that the field intensity is about half of it, what it was before. And you have more even color distribution, which is ideal because we don't have any enhancements. So we actually designed this. We were able to get the heat sink made and tested. The heat sink was created with a 10 millimeter radius. And the corona ring was 3D printed. We used SLA, Accurate 25, which is like a polypropylene material for SLA. And for making it conductive, we used Super Shield, which is just a spray-on that gives you that conductive coating. One of the legs specifically was fully coated, and this is used to make the direct connection to the heatsink. We did the same PD testing as before as we do for all of our assemblies. First, just starting off with the fans set and our fixture here to hold the heatsink and the corona ring. And with this, we found that we were able to get up to about 36 kV before we started to have PD, and that's with just a 25 millimeter spacing. We did push it until we saw flashover because the question is always how close are you riding to that edge? And with that, we were able to get up to about 49 kV before we saw flashover, which could be catastrophic for your converter. So it's a pretty large range away, even at 25 millimeters. So we selected this value to go through with our converter assembly. And here's just a nice image you can see where the flashover does occur. Like we said before, it occurs now from the ring down to the motor casing. So we tested this in the full assembly. This is just to show what it looks like. Inside of this cooling channel, we have one set of fans to push air in and the other side to pull it out. And we also tested it with the fans running. So here's the converter, the way that we assembled it. We have it sectioned off into zones. So the middle section here is all of our high voltage components. So the pre-charge, discharge, as well as the voltage sensor. And then all of our lower voltage components are the ones that are referenced to the midpoint or on the outside. We're able to sandwich everything in here and really try and push the air out of it, so it looks really like a building block. You can see here with our capacitors. So the power density, we were able to go from about 12 megawatts per cubic meter to 20 megawatts per cubic meter, which was about a 50% increase. We operated the converter. So far, we went to about 660 watts. We have a peak efficiency of 99.4%, and we've operated it in both DC-AC and DC-DC mode. So the takeaways from this is really that we can use the PCB-based bus to integrate several of the features that we want to get out of our medium voltage converter. Using the E-field-based design approach, we can significantly shrink all of our requirements. And using the capacitor card approach, we can get higher capacitance in smaller volumes. And again, stop by my bench. I'm at bench 44. We're in high power 2, and happy to talk to you about any questions or any feedback. Thank you.